Okay, so in section 1.2, the primary focus is going to be going over a few types of functions that we really need to be familiar and fresh with for this course. And I'll also give you a few reminders on certain techniques that we'll be using often. And then finally, we'll finish the section off with a brief review of the trigonometric functions, and that in particular, how to evaluate them at the fundamental angles. Okay, so let's get underway. So we'll start with just reminding you of the definition of one of the nicest types of functions you'll ever encounter, and that's a linear function. So a linear function is a function that's of a very specific form. It's a function that you can write down in a rule such as this. So look at what I've got. F of x is equal to mx plus b. So the m and the b, those are not variables, right? X is the only parameter or variable for this function, right? It's a function of the single variable x. However, we've got these two unknowns here. And really the reason there is just to stay general, right? M and b could be any real numbers, but it's to be understood that they're constant in this case. Okay, so you've got some number m and you've got some number b, and if you define a function in this form, you've got yourself a linear function. So what would the graph of a linear function look like? And if you remember, great, and even if you don't remember, you can probably guess just by the name what the shape of the graph of a function of this form might look like. So let's say we're going to graph the relationship y equals mx plus b in the Cartesian plane. Let's say we're going to graph that. Well, here's the origin, right, where the two axes intersect. You're actually going to get a straight line. Like I said, it's not a surprise based on just the name of the type of function, right? If it's a linear function, its graph is a straight line. And there's a couple of key features that we can really emphasize here. This number b that appears in the rule, whatever that ends up being, that is going to be the value on the y-axis where the line crosses through it, right? So this is going to go through the y-axis at the point 0b, because that's the point that has x coordinate 0 and a y coordinate of b. And this is referred to as the y-intercept. I'm just going to sneak that in down here. Okay, so that's what that point is. It's referred to as the y-intercept. So when you see a function written in this form, right off the bat, you know something about its graph. You know it hits the y-axis right at the point b. Another feature is of a line is if you pick any 2 points, I'm just going to pick these 2 points more or less at random for the sake of drawing the picture, but as long as you pick 2 distinct points in the line, you can follow along and do this. You could form a triangle by just going horizontal here and then going vertical here to make sure that it's actually a right triangle and you have a 90-degree angle in the bottom corner. And if I were to label the vertical edge as rise and label the horizontal edge as the run, well, then I can do the following. I can consider the ratio of the rise divided by the run. And if I do that, let's do this right here. I'll go rise over run. And it turns out this is always going to be equal to this constant m, right? No matter which 2 points you pick. So actually we have m is equal to rise over run. And just a reminder, this is referred to as the slope. You can say it's the slope of the line, or you can say it's the slope of the linear function. They're both perfectly fine. Okay, and one last thing I want to mention too, in the specific case where, because we mentioned that m and b could be any real numbers, right? If b happens to be 0, well, then that means the line is going to go through the origin. But what if m is 0? If m is 0, well, that means you've got f of x is equal to 0 times x plus b. You're really just going to get f of x is equal to b for every value of x. And in that case, you've got a constant function. Geometrically, that means you're going to have a flat line, a perfectly flat line. So if you have a slope of 0, that just means the line is completely flat. I won't add that to the picture right now, but I'll just mention it verbally. So, but I will write this down. Let's write this down. If m is equal to 0, then f is a constant function. And that's really just a really brief review of linear functions. A constant function is just a special case of a linear function. And a linear function is actually a special case of a slightly broader class of functions called polynomials, and that's what we'll define next. So a polynomial, that's our next definition. A polynomial p is a function of the form, well, let's read this carefully. We've got p of x is equal to, now what is this? This is, we see an a with a subscript n, so an is how you'd read this, an times x to the n, plus a with a subscript of n minus 1. Really, these subscripts here, the n minus 1, and then if I go further down to these two, you have a 1 and a 0. Those are just indices, just to separate, just to what it's really for, so you don't have to use a different letter for each of these numbers. Okay, so we've got an x to the n, a n minus 1 times x to the n minus 1, and so on, and you keep on going down until the indices get all the way down to 1, and you've got a1 times x, because really x is just x to the 1, so the index matches up with the power here. And then you've got a0, or often you'll hear people say this out loud as a naught. And this is really like a0 times x to the 0, because there's an invisible multiplication by 1 here, and anything to the power of 0 is 1. So that's the general form of a polynomial, where the only thing that matters here is that, well, n has to be a non-negative counting number. So n could be 0, 1, 2, 3, 4, and so on, right? Any of the positive counting numbers, or possibly 0. And these are called coefficients, by the way. Those a's with the subscripts, these are called coefficients. They can be absolutely any real numbers at all. Really, it's like a generalization of the m and the b in the definition of a linear function. We allow ourselves to have all these extra powers of x, and they can be multiplied by any real numbers. Okay, and in particular, this is called the constant term. It's a special coefficient. You can jot that down. It's called the constant term. Okay, so some remarks about this, and we'll get to some examples down at the bottom of the page, but for now I'll just make a few remarks. For a function like this, so all of these remarks are to be taken within the context of what we just wrote down, this function p. It's a polynomial of this form. The domain of a polynomial is all real numbers. Polynomials are defined absolutely everywhere. That's one of the nicest features about them. The next thing we would say is that each polynomial has something called a degree. Okay, so we'll finish that, fill this in. The degree of a polynomial p, which is denoted with this notation here. You just write deg and then put brackets around a p right after. So this is the notation that refers to the degree of a polynomial. And all it is the highest exponent that appears on x, right? So in this case, as long as this an is non-zero, this will be your highest power of x. Right? It's whatever is the highest exponent that appears on any of the powers of x. Okay, so, well, in specific cases, if the degree of p, let's write this down, we'll practice using this notation. If the degree of the polynomial p, let's say, is equal to 2, then we say that p is quadratic. Or you could say p is a quadratic. That's also fine, however you want to say it. And if the degree is 3, so we would say p, I'll just word this differently, p is cubic if its degree is 3. Okay, so degree 2 polynomials are called quadratics, and degree 3 polynomials are called cubics. It actually goes up further. If you want to take it further, you can. Degree 4s are called quartics, degree 5s are called quintics, and there's terms for all the other ones as well, or up to a certain point, but we're really not going to be interested in those. One last comment before we do some examples. I'll just want to remind you, in the case of remark 3 here, let's say you did have a polynomial with degree 2, then you could write it in this form, right? You don't need to have all these different coefficients. If you only had a degree 2 polynomial, you can just use a different letter for each of the coefficients. I can write it as a, so some number a times x squared, plus some number b times x, plus some number c, which would be the constant term here. So the graph of a function like that is actually a parabola, right? We mentioned that briefly last section, but I'll say it officially now. The graph of a quadratic is a parabola. And sometimes a parabola won't pass through the x-axis. That's a fact. But often it will pass through the x-axis at either 1 or 2 points. So in the case where a quadratic or a parabola does cross the x-axis, we can determine exactly where that's going to happen at points given by the so-called quadratic formula, which I just want to remind you what that is now. Okay, so the quadratic formula just tells you the places where the graph of this function crosses the x-axis, if there ends up being any. Okay, so remember what the formula is. It's just x is equal to, you take the coefficient of x, this middle term, the coefficient, and put a negative sign in front of it. Then you're going to go plus or minus the square root of, then you'll have b squared minus 4ac inside the square root, all over 2 times, and this is called the leading coefficient, by the way, 2 times a. All right, so that's the quadratic formula. And if it has no solutions, which will sometimes happen if the expression underneath the square root is negative, well then that just means that the parabola doesn't touch the x-axis at all. But if you do get solutions, then that just does tell you where the parabola touches the x-axis. Okay, so just a couple of examples. I could have something like p of x is equal to 10x to the 5 plus 3x squared minus 10. Let's say that's an example of a polynomial. And let's finish the sentence. Is a polynomial. And the degree of this polynomial, let's just sneak that in here, is 5, right? Remember, the degree of a polynomial is the highest exponent that appears on x, assuming that you actually use x for the variable, like we did up here, right? This was relative to here. But we've also used x for the variable here, so just look for the highest power of x. It's right here, x to the 5. So that means 5 is the degree of this polynomial. One last example of a polynomial. How about f of x is equal to 12x squared minus 2. That's another example of a polynomial, right? The highest power of x that appears looks like it's x squared, so you've got degree 2 polynomial. So this is an example of a quadratic. So it is a polynomial, and in fact it is a quadratic. Since the degree of the function f, I'll use the letter f in here because that's the name of the function, is equal to 2. And then one last example of something that's not a polynomial. Let's say I had g of x is equal to 4x cubed plus 3x squared plus the square root of x. That is not a polynomial. And why is that? Is it because I called it g and not p? No, of course not. That's not a problem, right? I can call the function whatever I like, and that doesn't change whether or not it's a polynomial. Like, for example, I called this function f, and because it fit the form of a polynomial, it's a polynomial. And in fact, we said more, it's a quadratic. But in this case, this function g is not a polynomial. The reason is because this x is not a whole, doesn't have a whole number as its exponent. If I wrote this as a power of x, this would be x to the 1/2, which is not, that's not allowed by the form of a polynomial up here. All these powers have to be whole numbers. So this is not a polynomial because of that square root. If I removed the square root of x and I just wrote 4x cubed plus 3x squared, that would be a polynomial. But because of that square root, it's not a polynomial. It's a perfectly reasonable function. There's absolutely nothing wrong with this as a function, but it just doesn't happen to be a polynomial. One last little comment. If I were to add, let's say, a square root onto the 2, in the previous example, so if I change this to f of x is equal to 12x squared minus the square root of 2, that doesn't harm the fact that f is a polynomial, and hence, and in this case, again, it's a quadratic. Because there's nothing wrong with square roots being built into the coefficients. The coefficients are allowed to be any real numbers at all, right? Even irrational numbers. But it's the variable. It's the variable that you use as a parameter here that cannot have any fractional powers. So it's the square root cannot be on a variable, but it could be in one of the coefficients, or in particular this case, the constant term. So I just made a little modification here because it doesn't harm anything. So you wouldn't change the fact that this is a polynomial and also quadratic.